Okay, good. Let's start. Last time we did Runge's theorem, and today also we will continue to discuss Runge's theorem. And yeah, so today the lecture session will not have much. We will basically discuss only Runge's theorem, and then we will have a discussion session where whatever questions you have, we will discuss. And also I will project some things from Conway and Rodin. Not really something that we can do, slightly advanced topic, but very related to the topics that we are discussing. So I thought I'll just point you to that. It's not something that we will do, or I mean, I don't know how to do those things. I mean, I have never looked at those things, and it may be beyond what we can do anyway, looking at the length of the proofs. But we will just see, the statements are not difficult to remember. So it all belongs to this circle of ideas, modern generalizations, we will see. So I'll just project the relevant pages so you can have a quick look, not really part of the syllabus. Okay, so we will recall what we have done last time and then continue. Let's get to the slides. I think I have started the recording, right? Yes, yeah. And I will start screen sharing. Can one of you confirm?
Yes, I
right?
can see the screen.
Yeah, yeah.
Yeah.
Yes. So, Roongas theorem we will continue. Yeah. So let's recall what we did last time. It's an important theorem, and what we did last time was the real crux. As you will see today, what we conclude the Runges theorem for a general open set. It's not difficult. It's just some basic topology, point set topology. So what we have done is the real crux of Runge's theorem, and we will have the general version today, but not much work to do. The real work is done. So last time we proved what is called Runge's theorem for compact sets, and the way I remember it, so this is a modern proof, as you can see. Runge's theorem, I think, is from 1885 or something, and some of these tools might not have been there, so our proof is certainly not the original proof. This is the modern version. I think this is one of the most accepted modern proofs. I promise that I will also give you the proof from Conway. Have a look at it if you have the book. Otherwise, one of the days we will come back and do it. Okay. So today I will not do it because I wanted to finish off the remaining parts of this circle of ideas. So there were four key ingredients. What were those? So I personally feel, and I think most of you will agree, that once we have names associated, it's easy to connect to that in our memory, and it's easier to recall. So we had this result which did not have a name, but we associated with Untitled theorem from functional analysis. So that was the first ingredient. So it's an immediate corollary to Untitled theorem. What did it say? It said that if you have a nonlinear space and if you have a subspace M, nonlinear space X and a subspace M, you would like to characterize M bar in terms of linear functionals. Linear functional meaning bounded linear functional or continuous linear functional, same thing. Bounded is same as saying continuous. So the characterization was that M bar is the intersection of the kernels of all those linear functionals, right? Intersection of kernel L, where L is a linear functional which is identically 0 on the subspace M that you have taken. So M bar is intersection kernel of L. L is in X star, L vanishes on M. One way was obvious. If L vanishes on M, and if L vanishes Yeah, if X belongs to M bar and if L vanishes on M, then L vanishes on M bar is clear just by the continuity of the linear functional. Other way we use the Hahn-Banach theorem. Other way we use Hahn-Banach theorem. So M bar is contained in this intersection is obvious continuity, and the other way we proved if something is not belonging to M bar, we showed that there is at least one linear functional which is 0 on M but not 0 on that point. This was the first ingredient. The second ingredient, we only stated we couldn't say anything in terms of proof because the measure theoretic, the rigorous way of stating it, I could not have done. It is what is called the Rees representation theorem, which said that C0x, where x is locally compact Hausdorff, then the dual of C0x, continuous linear functionals on C0x, is isometrically isomorphic to regular complex Borel measures on X. You can put a norm there and it's an isometry. But for us, X is going to be a compact set and C0X is nothing but continuous functions on the set. And with the subnorm, that's our norm linear space. It's in fact a Banach space. It's complete with respect to that metric. And the duals are characterized by these nice measures. This was the second ingredient. Third ingredient was just at one place. It's just Fubini's theorem. You can interchange integrals. That was justified in our context because both our integrals were on compact sets. So interchanging was not a big deal. That is Fubini. So these are all ingredients which have nothing to do with complex analysis, right? One is from functional analysis. It was about continuous functions on a compact set. The other is Rees representation theorem. So it's measure theoretic again on continuous functions. There's no complex analysis. There's no holomorphicity. Fubini's theorem is a general theorem from measure theory. There's no complex analysis. But Runge's theorem is a complex analysis theorem. So the fourth ingredient is where complex analysis came in. And this is what I call compact CIF. Once again, there's no standard terminology. There's nothing called compact CIF. It's just my way of remembering it. The point is usual Cauchy integral formula. Cauchy integral formula. You will have a formula f of z equal to something whenever the curve is homologous to 0. Whenever the cycle is homologous to 0. Here, given a compact set and an omega containing that, yeah, is there a question? Yeah. So here the point is that we can choose a gamma such that the Cauchy formula is true, right? So in general, we say that whatever cycle you choose, if it is homologous to 0, then you have the Cauchy integral formula. Fz times index is something. Here the point is we can choose an appropriate cycle so that the Cauchy formula holds true. So we chose a cycle. This is the part where I skip the proof, saying that, pictorially it's easy to visualize, but writing it down is not so easy, so I will skip it. Please have a look in one of the textbooks, both Conway and Rodin has more or less, they have more or less a similar proof. Have a look at it. Otherwise we can discuss. Yeah. So this was the fourth ingredient. And what was the basic structure of the proof? I think we had a longish discussion in the last discussion session, but very quickly, the basic structure of the proof is the nonlinear space X that you take is CK, continuous functions on. So what is there in Runge's theorem for compact sets? You have a compact set given in the plane, and F is holomorphic in an open neighborhood of X in an open set containing K. K is a compact set. Omega is an open set containing K, and F is holomorphic in omega, which contains K. And you want to say that F can be approximated uniformly on K by rational functions. Not just that, these rational functions, the poles can be prescribed in advance, pre-assigned poles. And how is this pre-assignment done? You choose a set which meets each component of, which intersects with each component of S2 minus K. The extended complex plane, the Riemann sphere, the complement of K in that may have several components, and this set prescribed set A should have one point from each of these components. So the compact set K is given, and your space X, the nonlinear space X is CK, and those functions which can be approximated nicely, you call it M, and then you wanted to say that an F holomorphic F on omega belongs to M bar. And this is where the first ingredient came. We have a characterization of M bar, and which is in terms of linear functionals. And that's where the second ingredient came, because linear functionals on CK star, linear functionals on CK are in terms of measures on K. That's where the second ingredient came. And then in terms of the hypothesis can be interpreted as a certain integral with respect to a measure on K being 0. And we have to conclude that integral f d mu is 0. And this is what we achieved. We achieved it for one particular function that we have written down, and using that function and using compact CIF and using Fubini, we proved that integral f d mu is 0. Okay, so too many words maybe, but something that we have already done, only trying to recall. So yeah, it's a conceptually somewhat of an advanced proof, but I deliberately did this proof because this is one of the standard proofs, and it's a beautiful proof. Okay, so if you haven't fully followed, that's okay. Go through it again and again and try to work out some examples. It's okay to have some confusion, but we will discuss it again if you want. Today we will continue discussing Roongas theorem. We will deduce the general form from the compact version, and the only result that you need is what I sent you, that screenshot that I sent you on WhatsApp. You know, I sent it in some other context maybe, but this is where it's really going to be used. So we will recall the result and the proof I had sent you on WhatsApp from the book, and that's all that you need. So the Runges theorem for compact sets plus what I call compact exhaustion, meaning any open set omega can be written as a countable union of compact sets satisfying those properties. That is called compact exhaustion. And once you have Runges theorem for compact sets, and once you assume compact exhaustion, then the general Runges theorem will follow. There's nothing more to it, so that's easy. So we will do that. And as usual in the discussion session, we will discuss whatever questions you have. We will also discuss a few. So last class I noticed projecting something on the screen is quite an easy thing to do. And in this aspect, I feel online teaching is better than real teaching in an actual classroom, where in order to point to a particular page from a book, all of you should have the book, I should have the book, and then I should refer you to that. Here I can project it, and all of you can see it. So we will project 1 or 2 pages from these books, and I will indicate some general results. In fact, one general result, which is a natural, much advanced extension of Roongas theorem. And as I told you earlier, some of these are much beyond the scope of this course. We will only briefly mention this. Just to have, just to see what is happening. So these are things which I have never looked at. I have never looked at the proof before, not even now. But that's not the point. I just wanted to say, these things are there. Okay. So I think we had this discussion on WhatsApp after the last class that why we take S2 and not C. And I said that the set having the point infinity, that leads to some nice results, because what are holomorphic functions with a pole at infinity? Pole only at what are meromorphic functions, or no, what are rational functions with pole only at infinity? That is just a polynomial, right? So approximation by polynomials, you can deduce some nice corollaries. So I have just put it in the screen. We have already discussed this over WhatsApp after the last class, but let it be part of the slides as well. So that is this slide. So suppose K is a compact set such that S2 minus K is connected. So in Roongas theorem for compact sets, S2 minus K may have many connected components. By the way, we are not assuming K is connected. No? K can be, disconnected. That's why in many problems, it will be important to take K not connected. We are not assuming anything about K being connected or omega being connected. That's where the power of Runge's theorem actually comes in. So assume S2 minus K is connected. We will see later that this is same as saying K is simply connected, but that's later. So assume now that there's only one component of S2 minus K, and in that case, we can apply Runge's theorem. So S2 minus K is, of course, it has the unbounded component. So if it has only one component, it is just the unbounded component. And the set A is a singleton, and this point is any point from the unbounded component. So any function which is holomorphic on an open set in C containing K can be uniformly approximated on K by rational functions which have poles only in A, but A is a singleton, so which have poles only at that point, point in A is a singleton. So this is a corollary. In particular, you have the freedom, choosing A is up to you. The only condition which you should not, deviate from is that A should meet each of its components. Now there's only one component, so A should have one point from this component, that's all. Which point is up to you. So in particular, you can choose A to be the point infinity. And therefore, this line will say that any holomorphic function on an open set containing K can be uniformly approximated on K by rational functions which have a pole only at infinity. In other words, it can be approximated uniformly by polynomials. So it's a nice generalization of Weierstrass theorem. Right? Weierstrass theorem said that on a compact interval in R, any continuous function can be uniformly approximated by polynomials. Such a thing is not true for complex analysis, as we have seen, right? You remember this? We proved that if you have holomorphic functions and if they converge uniformly on compact sets to a function f, if there's a sequence of holomorphic functions fn, and if there's a sequence of holomorphic functions fn, and if they converge uniformly on compact sets to a function f, then f is also holomorphic. So any continuous function can be uniformly approximated on compact sets is certainly not true, because limit is automatically holomorphic is something that we have proved. But this is what we get, that if you have a holomorphic function on an open set containing K, compact set, where K has this property that S2 minus K is connected, then we can do this. It can be approximated by polynomials uniformly on K. If S2 minus K is not connected, this cannot be done. I mean, in the sense there's always one function that you can write down which cannot be approximated by polynomials. Why is that? Because if S2 minus K is not connected, then there is of course the unbounded component, because K is bounded. There's of course the unbounded component, but there's also one more component which is bounded, right? It's not connected. So there are at least two components. So there's a bounded component, V. You can take a point A in V and you can consider the function 1 by Z minus A. And this cannot be uniformly approximated by polynomials. So one picture to keep in mind, we will give a proof of this in the next slide, a general proof, but the one easy picture to keep in mind is you take the punctured disc, and puncture at the origin, punctured unit disc, let us say, and you consider the function 1 by z, right? Now the question is, you want a compact set, so you take, an annulus centered at 0, a compact annulus centered at 0, and you take 1 by z, and you want to say that this cannot be uniformly approximated on the compact annulus by polynomials. And one standard proof in this particular example is you can take a circle in the annulus which is centered at 0, and suppose throughout this compact annulus you can approximate 1 by z by polynomial. So 1 by z is limit Pn. You can integrate on this circle inside the annulus. So integral of limit Pn, this circle is also compact and it is uniformly convergent. We are assuming Pn's uniformly converge to f. So limit Pn, integral of limit Pn on this circle is limit of integral Pn, but integral Pn is 0 because Pn's are holomorphic. So Cauchy's theorem. So limit of integral Pn is limit of 0, which is 0. Right hand side is 0. Whereas the left hand side is integral over a circle of 1 by z dz, which you know is 2 pi I. So that's a contradiction to the fact that, a contradiction to the assumption that you can uniformly approximate it by polynomials. Okay, let's see one more proof which is slightly more general using maximum modulus theorem. This is a proof that Rodin gives, Conway also gives. So that is there in the next slide. So if you consider this function is holomorphic on an open set containing k, but it cannot be uniformly approximated on k by polynomials. Here is another argument using right, the earlier argument using integration, I used that you can take a circle inside, you can take a curve inside the compact set, etc. So that they, some thought has to be given. Can you always take such a curve and do this integration, etc. Therefore, here is a proof via maximum modulus theorem, which doesn't take a curve or anything. So it's slightly more, it's a better proof in that sense. Okay. So let's prove something more general. So if S2 minus K is not connected, right, in Roongas theorem, you said that this set A of pre-assigned poles, prescribed poles, has to meet each component, and essentially this claim is that it has to meet each component is a condition that you cannot further relax. It has to meet each component at least once. More than once, if it meets, okay, you don't care. But once it has to meet, and this condition cannot be relaxed. It's the same proof as this, the proof of this, right? Because here you are choosing something from a component where you are assuming, right, the function cannot be uniformly approximated by polynomials. Polynomials have poles at infinity. So you are assuming that approximating by polynomials, meaning approximating by rational functions which have a pole only at infinity. There's no pole from the bounded component. So A does not meet the bounded component, and then there's a contradiction. Similarly, you can show that A has to meet each component. Otherwise, there's a contradiction. That's what we will do slightly more generally. More generally, we cannot relax this condition in Roongas theorem. What was the condition? The set of prescribed poles, pre-assigned poles A of the approximating rational functions in Roongas theorem has to meet, has to intersect every component of S2 minus K. This condition cannot be relaxed. What happens? Otherwise, let V be a component of S2 minus K such that A does not meet V. Right? It has to meet every component. Otherwise, there is at least one component whom A doesn't meet, right? Which A does not intersect. So take such a V and choose a point A in V and consider the function like similar earlier function fz equal to 1 by z minus A. This is holomorphic on an open set containing K, right? On a small open set containing K, this function is holomorphic because A is in V, A is outside K. So there is a small open set containing K where this is holomorphic, and we want to say that this cannot be approximated by rational functions whose poles are only in A. This cannot be approximated by rational functions whose poles are, all whose poles are in A, uniformly on K. So argument uses the word to remember is MMT, maximum modulus theorem. So choose the maximum of modulus of z minus A for z in K. Such a maximum exists because K is compact, call it M, and choose a rational function R, all whose poles are in A does not meet V, that's where the contradiction is going to come. All whose poles are in A, and suppose you can approximate. Okay, so with this M you argue. So take the maximum over K and take 1 by m and let this be your epsilon, and there is a rational function such that the distance is less than 1 by m. This rational function is such that poles are in A and A does not meet B. Okay, so this can be done. If we could have relaxed this condition, then that means this can be done. So do this for all z in K, it's uniform. Okay. So by cross multiplying and writing, what is Fz? Fz is 1 by z minus a. So z minus a times Rz minus 1 modulus is less than mod z minus a by m. Just cross multiplying. So mod z minus a Rz minus 1 is less than mod. So there will be a by mod z minus a less than 1 by m. So that has come here, mod z minus a by m. But what is m? M is the maximum of mod z minus a over k. So mod z minus a is less than or equal to m, so it is less than or equal to 1 for all z in k. All of you are with me? So this is, suppose we assume that we can approximate by rational functions with this relaxation, then we end up here for this particular function that you have chosen. Function being 1 by z minus a. For that function, you've got a rational function. And remember, this rational function is holomorphic on V because its poles are in A and A does not meet V. So this is holomorphic. So this is a holomorphic function. Therefore, this is a holomorphic function. And this holomorphic function modulus is strictly less than 1 because this is strictly less than 1 throughout K. Now, in particular, see K contains a boundary of V also, right? V is a component of S2 minus K and V is open, and the boundary of V will be touching K. I mean, it's part of K. So this condition is true for all Z in K and in particular for the boundary of V, and you are going to argue with V now. See, something on K is given and you are going to argue with V. Let's assume that V is bounded for this argument. So I'm dealing with a bounded component. So assume V is bounded and let's finish the proof there. If V is bounded, then of course V union, the closure of V, right? The closure of V is also bounded and closure is of course closed. So V union boundary of V, which is nothing but the closure of V, this is compact. And this particular function Z minus A times Rz minus 1, this particular function is holomorphic here, and therefore it is continuous and therefore it has a maximum. It has a maximum on V union boundary of V, but it's also holomorphic there. So therefore the maximum has to be attained on the boundary of V. So because it is compact, therefore this attains its maximum there, and by MMT this maximum has to be on the boundary. Maximum local maxima cannot be there on the open part, on the open set. So by extreme value theorem, if the maximum is attained, it has to be on the boundary. So what is the conclusion? This, it's not P here, it is R. This function Z minus A Rz minus 1. What is the conclusion? This attains the maximum on the boundary, and on the boundary it is less than or equal to 1. So the maximum on V union boundary of V is strictly less than 1. Right? That is a conclusion from MMT with EVT, that the maximum of this function on V union boundary of V is strictly less than 1. But then there's a contradiction. The contradiction is that at Z equal to A, this is 0. Because Rz has no pole at A, so this is 0. Therefore, this is minus 1. Modulus of that is 1. 1 is strictly less than 1, and that's a contradiction. So the contradiction came because you assume that your set A does not meet V, and then you can choose at least one function. We chose 1 by Z minus A, which cannot be approximated by rational functions with poles only in A. Okay, so we have assumed that V is bounded because I think this argument used that. I wanted a compact set, therefore the EVT could have been applied, and then I appeal to MMT. So if V is the unbounded component, then this is not quite true. In fact, I was thinking about it yesterday and I don't have a I don't have, a crystal clear argument for V is unbounded, but we will discuss it. I think discussion will clarify and we should have a crystal clear argument. So for now, since I didn't think about it so clearly, this is one argument or maybe a possible argument, let me put it that way, and I invite suggestions. If V is the unbounded component, one thing that you can do is, right, when V is the unbounded component, there's a problem with this argument. Though boundary of V, we may have a boundary which is contained in K, that part is okay, but I cannot say that together with the boundary whole thing is compact. So even if I take a point and take a compact set contained in the unbounded component, this argument will not go through exactly as it is because it may have another boundary which is not touching K. So only on the boundary that is touching K, I can say it is strictly less than 1. I don't know the value at the other boundary. So there is an problem with that argument. So if V is the unbounded component, one way to argue would be you make a suitable, right? I mean, anyway, arguing with the neighborhood of infinity is by making a transformation. Z going to 1 by Z kind of a transformation. So we may argue with a suitable transformation. I could suitably take, Z going to 1 by Z minus a point, or even 1 by a multiple of M times Z minus a kind of a thing. Suitably, you can make a transformation which takes the unbounded component inside K and the holes in K pictorially, right? So K and the various bounded components of S2 minus K and K put together, the unbounded component can be transformed inside this, and then our previous argument works with any of these bounded components. So something like this should work, and I think the unbounded component case has to be converted to the bounded component case. Or maybe, if we take a function, for example, if so, okay, so one more idea maybe to argue directly will be just like we took 1 by Z minus a here, a nice function that one can think of, some simple function should do. So if A does not meet the unbounded component, right, K is compact, so K is contained in a bounded disk and you have this unbounded component, and if A does not meet there, you can take a nice polynomial, you can take one of the simplest polynomials, you can take fz equal to Z itself. And I think we can argue that fz equal to Z cannot be uniformly approximated on K by rational functions meeting only the bounded components.
fz, we can't take the sequence to be Z itself, right?
Yeah, because it doesn't meet anything in the unbounded component. So if the sequence is Z itself, it has a pole at infinity, and the set is not meeting. We are assuming, right? Suppose not. So we are assuming that A does not meet anything in the unbounded component. Therefore, Z is not an option. It's not a rational function. It's not an allowed rational function.
All right.
So Z itself will do, but then as you also hint, we have to give an argument. So if we can give a crystal clear argument using Z, which I'm sure will work, but it's a question of writing down that argument clearly. And then, instead of this, I could have written that itself. So the way I'm thinking is, if you take Z, the obvious thing would be Z itself, but that doesn't work. Now, what are the rational functions which are what are the rational functions which have no pole at infinity? Let us say we have to deal with other points in the unbounded component also. But what are the rational functions which have no pole at infinity?
I think P by Q, where Q has a greater degree, strictly greater degree.
Absolutely, right? P by Q, where Q has a greater degree. So yesterday
Yeah.
I was thinking we can use the term degree of the rational function is less than or equal to
-1.
less than or equal to -1 or 0 also. Constants are allowed. Degree less than or equal to 0. No?
I
Constant,
think, yeah,
constant is okay. But
something like 2Z plus 1 by 3z plus 5 is also allowed, right? Yeah.
That is also allowed. That's also degree 0. Yeah, no, I'm making a non-mathematical statement because then I in my own mind I always need words. Only then I can remember, because otherwise I cannot remember things. So I use the word degree, and then when I was typing degree, I had a doubt. I mean, in my mind, degree was degree of the numerator polynomial minus the degree of the denominator polynomial. But is there such a definition? So I went to Wikipedia. And I checked degree, and Wikipedia says degree, is not a uniformly used term. So some people use degree in this sense, the sense that I thought. But maybe, I mean, see, my area is number theory, and as a number theory, I should have remembered, or maybe, unconsciously, that's why I got a doubt about this degree. I'm talking something which is completely irrelevant. I mean, don't take it seriously. That a more natural notion of degree, certainly in the kind of number theory that I do, I don't know how I forgot that for a moment, is the maximum of the degree of P or Q. So I will not use the word degree in this thing. So I will say exactly as Arjun said, that consider the degree of the polynomial, and Q should have a higher degree than degree of P. Right? So these are the rational functions. So now, so you can take a z minus a by z minus b, right? You can take z minus a by z minus b. This has no pole at infinity. So where are the poles of z minus a by z minus b? It's only polars at z equal to b. There's no other pole, no? Z minus a by z minus b, the only pole is at b. There's no pole at infinity. So if mod b is high enough, then this is not allowed. If mod b is small, then this is allowed. If mod b is small,
Yeah.
b could be in the bounded component. See, first of all, suppose there is only unbounded component, then there's nothing to prove, right? Then it's obvious what we are trying to say. Suppose there is only unbounded component, there's no other component, then K has no holes, no pictorially, right? If there's no unbounded component, then you can take Z, and it is clear that Z cannot be approximated with rational functions with no poles in the unbounded component, because if no pole is there in the unbounded component, then the only poles are inside K. But if there is a pole inside K, of course it cannot approximate Z, because it will blow up. No. So then there's nothing to do. So the only argument required is if it has a bounded component and an unbound component, of course, is there. If there are also bounded components, only we need an argument. And then when you take z minus a by z minus b kind of a rational function, we can also take its squares and sum up, etc. That's how we will form, a Lorentz, a polynomial, a power series kind of thing. But the basic building block is z minus a by z minus b. If mod b is small, if mod b is such that if b is from the bounded component, this is allowed. If mod b is big so that b is in the unbounded component, this is not allowed. Using this much info, we should be able to say that z cannot be written like that. But these are just words. It's not, something clear enough that I can type it. So let's distill the correct argument from this. Something like this should work, and then I don't need this transformation thing. Transformation thing also I'm not completely satisfied. I mean, it's not completely clear in my mind. This is just an idea, but one of these things should work. But the point is, we should argue with the unbounded component also. So it's essentially MMT. For bounded component, the argument is perfect. Okay, let's leave it at that. We'll come back to it. But what is slightly confusing in my mind is clear to you, no? Rajiman already discussed. Omkar, are you there?
Yes, sir.
So I have made it clear that there is a slight confusion in my mind at this stage, right? That's all that I am trying to convey.
Yes, yes.
Yeah, so that when we discuss, it will be clear. I think either we can argue directly with Z itself and we should finish off the proof, or this thing that I have written down, but it's not pakka. I mean, in the slide also, that confusion is clear, which is genuine confusion. This was a last minute thing, so I did not really spend time, and I didn't want to spend too much time either. I thought I will take your help. Okay, others also, I hope, have followed. Is Chirag is not there today? Ariman as his class. Okay, maybe I don't want to, I will tell him. He's being this is alphabetical order, I'm sure. Yeah, Chirag is not there. Okay, so Saurav Kumar is not there. So I do notice some regular absentees. So let me do one thing. Let me download the attendance list. Yeah, once in a while I'll download the attendance list because I would like see 1 or 2 classes if you miss I can understand, but it should not be a regular feature. It's not that's not correct because we are dealing with so many difficult things. So even if you don't fully follow in the class, still coming to the class is important. Then you know what to ask me later or what to discuss with your friends, etc. So yeah, so I do insist that students do attend the classes as much as possible. Okay, going back to this, I don't have my mobile with me. I hope there's no message on WhatsApp. I don't have it with me. And what is the time now? 10:15. So yeah. So let's come to the So one more remark. This is okay. So we wanted to say that A has to meet each component that cannot be relaxed, and we gave counter example indicated at least in the unbounded component case. But if you look at the proof, which is the correct thing to do, we have to show. See, if you don't have that assumption, then you get this contradiction. We have to show that. But another way of convincing ourselves, though that's not a proof, is that we can look at our proof of Roongas theorem for compact set and see what we have done. That's also one more way of going back to the proof. Since our proof was slightly advanced, it's good to go back to it as many times as possible. So from that perspective, let's look at the proof also. We had to show that the holomorphic function defined on S2 minus k like this, right? Integral over k d mu zeta by zeta minus z, where mu is a nice measure that you have chosen corresponding to the linear functional that you have taken. And you have to show that this particular function is identically 0 on S2 minus k. This was the crux, right? This particular function is holomorphic by our general geometric series argument and Weierstrass test, etc., etc. We knew that this is holomorphic wherever it's defined, and that is S2 minus k. And we had to show in the proof, the crucial step was to show that this is identically 0. And how did we show this is identically 0? You take the components of S2 minus k. So these are several S2 minus k is open. So each component is automatically open. And on all these open sets, you have to show that H is identically 0. So arbitrarily, you pick one open set and you have to show that it is identically 0 on that picked chosen open set. How did we show that? You take a point from that open set and you take a neighborhood of that, an open disk around that completely contained in that. That you can do because V is open. And on that thing, you expand this using geometric series. And in that expansion, the terms those are coming have, in that, how are you choosing your open disk? The open disk you are choosing around the point in A. A meets each component. So A meets V, A intersects V. That point you choose. And around that point you take an open disk. So that the meeting point you have crucially used in this part of the proof. So the point that it meets you have taken, and you have taken an open disk around that, and there you do the geometric series expansion. So each summand is a rational function with poles precisely there, and our hypothesis amounted to saying integral r d mu is 0 whenever r is a rational function with prescribed poles. So each of the summands, the integral is 0. And it's a uniform convergent thing, and therefore the integral of h is, therefore h is the integral of 1 by zeta minus z. It is 1 by zeta minus z that we are expanding as geometric series. So integral of 1 by zeta minus z is 0. In other words, h is 0. So where is h 0? H is 0 on a small open disk around this chosen point from A, capital A. And therefore h is 0 throughout V, because we know that it is holomorphic and by the identity theorem. This was the argument. So here we had two arguments. If the point is not infinity, we had the argument using 1 by zeta minus z. And if the point is infinity, we had the argument using 1 by z minus zeta. With the negative sign, you will expand, and and we finished up. So the proof trick was the same. So the point is, this meeting point was very crucially used at this step. We use the point and expand along that point, and only then, that rational function hypothesis, integral r d mu is 0, we could use only if we expanded along that point, so that it met in each component was crucially used. But of course, this is not good enough. This tells us strongly that we cannot relax that thing. But in order to show that you cannot absolutely relax, there's no way you can relax, we have to give a counterexample. But this also strongly indicates to that thing, because we have seen how crucially it is being used, and we cannot see another way of doing that proof. But again, theoretically it's possible that maybe there's another proof, this is not the only proof, etc. So we have to give a counterexample, which we have given. And this last step crucially made use of the point in the meeting point, the common meeting point. Now we state the general Roongas theorem. So this is the statement. Next paragraph is the statement. The common version, as you will see, there's no real complex analysis input here. All the complex analysis, all the real ingredients from functional analysis, measure theory, everything was done for Roongas theorem for compact sets. So that was the real thing, the real substance. The meat was there, and this is just putting some more a little bit more to that thing, but this is pure topology. And topology at a very basic level, there's nothing much. Okay, so let omega contained in C be an open set, and let A be a set which has one point in each component of S2 minus omega. Okay, so now you don't have a compact set and an omega containing that, you have only an open set, and you are looking at the complement of omega in the extended plane, and you are looking at its components, and the set A has to meet each component. This is the crucial hypothesis. Assume F is holomorphic. Omega is open, so holomorphic makes sense. F is holomorphic. Then there exists a sequence of rational functions Rn with poles only in the pre-assigned, in the prescribed list A, such that Rn converges to F. And what is convergence in complex analysis? If we don't say anything, if we just say functions converge, that means converges uniformly on compact subsets. So I'm not claiming uniform convergence everywhere. It's not point-wise convergence either. It's better than point-wise convergence. It's not as rigid as uniform convergence everywhere. It's somewhere in the middle. Convergence is uniform on any given compact set. You give me a compact set, I know that my convergence is uniform there. This is the correct notion of convergence and complex analysis. So Rn converges to F in the complex analysis topology, meaning it converges uniformly on compact subsets of omega. This is Roongas theorem, and the proof is easy. Of course, like earlier, the important special case to keep in mind is S2 minus omega is connected, where we will take A to be singleton infinity. So this result would say what? If omega is such that S2 minus omega is connected, as we will see later, this is same as saying omega is simply connected. So if omega is simply connected, which we haven't done, so let's assume, let's use the wording that S2 minus omega is connected for now. So if omega is open such that S2 minus omega is connected, and if you have a holomorphic function, then the special case tells you, if S2 minus omega is connected, then the special case tells you that F can be approximated by polynomials. And the approximation is good enough in the sense that the approximation is uniform on compact subsets of omega. So any holomorphic function on omega has the property that S2 minus omega is connected. Then any holomorphic function on omega can be uniformly approximated by polynomials uniformly on compact subsets. Okay, so this is an important corollary. And one more remark is that earlier when we dealt with compact sets, S2 minus k had at most countably many components, and Argument indicated a quick proof in our discussion session, which is that each of this component, these are all open sets, and everything has a point with both the coordinates rational. So you can use countability of rational numbers or rational tuples and conclude that S2 minus K had at most countably many components. But S2 minus omega can have uncountably many components. And the nice example from Rudin is you can take a compact set which is uncountable and totally disconnected. So it has uncountably many components. So you can take a compact set with uncountably many components and take its complement to be your open set. Therefore, by definition, the complement of that open set is this compact set which has uncountably many components. Throw in infinity also. And you know that such compact sets exist. For example, Cantor set is one such thing. So this is Rodin's example. So this can have uncountably many components. But our proof doesn't make use of that. In fact, in earlier thing also that, we knew that it is right S2 minus K when I argued in our proof, though it was only countably many components, we never used that fact. We took an arbitrary point and we argued with that. Even otherwise, even if the proof was only for countably many, which was not the case, it doesn't matter, as we will see in our proof here. It can have uncountably many components. That's okay. So general version follows from the compact version by compact exhaustion. I don't know. I think I've seen this term compact exhaustion somewhere, but I don't know for sure. Rudin doesn't say it. But what I mean is, that's why I put quote unquote. What I mean is what I send you on WhatsApp. So which is that you can choose Kn, n natural numbers 1, 2, 3, etc. contained in omega. These are all compact sets such that these three properties are true. Each Kn is contained in the interior of Kn plus 1. We don't really need this fact in this proof that it's contained in the interior. Contained in Kn plus 1 is enough. But we know this. Interior, contained in the interior of the... Yeah, this is interior. What is interior? Set of all interior points. The maximal open subset for each n. Every compact subset of omega lies in some Kn. You can choose such Kn such that every compact subset lies in some Kn, and every component of S2 minus Kn contains a component of S2 minus omega for each n. This property we are going to crucially use. All these three properties we will use. Okay, every component of S2 minus Kn contains a component of S2 minus omega. So what is the picture? If you have omega, so pictorially, omega is something like an open, one good picture to keep in mind is an open annulus, let's say centered around 0. So omega is something like that, some open annulus. And if you take a compact subset inside that, pictorially you can think of, two obvious kind of compact sets. One is a compact disk inside that compact annulus, in which case its complement is everything other than that thing, which of course contains, and what will be the complement of, S2 minus, no, what do we want to say? No, sorry. So it's not about any compact set that you choose. It's about these compact sets. Yeah. So if you take an open annulus, these Kns, for example, you can think of them as the compact annuli inside that open annulus. Compact annulus you can take inside, right, with smaller and smaller, right? If you have 1 to 2, let us say the radius open annulus, you can take 1 plus epsilon and 2 minus epsilon and the compact annuli, and you can take it for various 1 by n, epsilon 1 by n. That will be, the picture to keep in mind, which will have all these properties. Each compact subset will contain in one such, and then if you take a component of S2 minus Kn, it will be the unbounded component together with the inside disk, but that contains a component of S2 minus omega, right? The unbounded component of S2 minus Kn contains the unbounded component of S2 minus omega. The bounded component of S2 minus Kn contains a bounded component of S2 minus omega. So that's a picture to keep in mind, and this can be done very generally, abstractly. You don't need such a nice picture to keep in mind. That was the point of compact exhaustion. So it needs a proof. Not very difficult. I have sent you the proof. If we want, we can discuss it at some other point, but let's finish off the theorem. So by the last condition above, so what is the condition on Roongas theorem? This pre-assigned thing meets every component of S2 minus omega. And by this compact exhaustion thing, each component of S2 minus Kn contains, every component of S2 minus Kn contains a component of S2 minus omega. So if A meets each component of S2 minus omega, then A meets each component of S2 minus Kn. Right? If A meets each component of S2 minus omega, then A meets each component of S2 minus Kn. And therefore, we can apply Roongas theorem for compact sets. Where are we applying? We will apply it for Kn. And you will get some rational function so that the distance can be made arbitrarily small. And you argue for 1 by n. Take epsilon to be 1 by n. So you can get a rational function, call it Rn, whose poles are only in A, such that Rnz minus Fz, the modulus is less than epsilon. Epsilon is 1 by n throughout Kn. This is the theorem that you have done. If K is an arbitrary compact set, by the second condition, that is contained in some Kn. Therefore, K is contained in some Kn for some n. And thus K is contained in Kn for all n bigger than or equal to n by the first condition. So if K is an arbitrary subset of omega, there is a stage n beyond which K is contained in all those K's. This is part of compact exhaustion. And therefore, what have you proved? For all n bigger than or equal to n, we have for all z in K, and n does not depend on z. N depends only on compact exhaustion. So n does not depend on z. For all z in K, the same n will work. You have Rnz minus Fz is less than 1 by n. This is true for all n bigger than or equal to n and for all z in K. So you choose n such that K is contained in Kn for n bigger than or equal to n. It does not depend on z, and you have this approximation. So convergence is uniform on K. So this is what you had to show, that Rn converges to F uniformly on compact subsets. You give me a compact set, I have shown you that convergence is uniform on that compact subset. Okay, so there's nothing much to this proof. It's just compact exhaustion. So Roongas theorem for compact sets together with this elementary compact exhaustion argument proves for you the general Roongas theorem. So on any omega open, any holomorphic function there, you have a sequence of rational functions in a nice fashion because you can pre-assign the possible list of poles. Possible list of poles. I'm not saying that these Rns have to have poles there. All those, it doesn't have to have poles in each element of A. Of course not. But if there are poles, they have to be in A. And such that Rn converges to F and the convergence is good, it is uniform on compact subsets. So this is the general Runge theorem. So we will stop the class and a few topics let us discuss quickly. So there's a notion of polynomially convex hull. I will just project the page. I can verbally say that also. This is not very difficult notion, but it naturally comes in the context of the proof that we have given using MMT that we cannot relax the condition on A. So that naturally leads to this notion. So Conway says that. So we will project that page. And then there is a theorem called Mergelian's theorem. Mergelian is a mathematician. Mergelian's theorem, that's a modern theorem, 1961, I think. And I saw this in Wikipedia article about Roongas theorem first, and then when I checked the index of Rudin, it's there in Rudin also. So it's theorem 20.5. So it's at the very end of Rudin after, developing a lot more other stuff which is not part of our course. So we cannot do this. Even if we have time, we can't do this because it covers a lot of other things. So we will just see what the theorem is. See, in order to read the statement of the theorem, you don't need anything. You need only the notions that we have. It's a proof that is difficult. And proof I saw in Rudin is several pages, 3-4 pages. And it occurred to me that in a basic textbook, I don't think I have ever seen a proof that runs into 4 pages, 4 printed pages in a dense book like Rudin. Right, all these results that we have covered till now is half a page proof in Rudin. and this is 3-4 pages. Okay, it is 3-4 pages can be remembered because this reference to the statement of the theorem is 390, and soon after the proof there is an exercise that is 394, and that also we will project. Okay, so this is what we will do, and then we can do general discussion. So let's finish the class here. Let me stop this recording.